We propose learning distributions over control sequences for MPC using normalizing flows. The learned sampling distribution generates goal-directed and obstacle-aware control sequences. We additionally propose an approach for adapting the sampling distribution to novel environments. Consider the following navigation problem. We frame this as finding a control sequence that minimizes the expected cost. We consider cost functions parameterized by ρ. For instance, ρ may determine the trade-off between distance to goal and control sequence smoothness. Popular sample-based MPC methods iteratively update a nominal control sequence using Gaussian perturbations. This process is only as good as the samples. If we now add obstacles, the samples are high cost. Iteratively resampling leads to us becoming stuck in a local minima. In contrast, samples from our proposed learned sampling distribution are shown on the right, showing qualitatively different trajectories toward the goal while avoiding obstacles. How should we train this sampling distribution? Intuitively, we want a sampling distribution where the likelihood of a sample is related to the cost while maintaining diversity. We formalize this as Bayesian MPC, first introducing optimality variable O. The goal is then to find a posterior distribution over low-cost control sequences. We use variational inference to approximate this posterior, minimizing the KL divergence between our approximation and the true distribution. This results in the following objective, where we minimize the cost of samples while also maximizing the entropy. Now I will go through our proposed sampling method. The inputs are the start, goal, cost parameters, and environment. We use a variational autoencoder to encode the environment to a latent representation H. We use a normalizing flow as the latent space prior learned during training. We encode H, the start, goal, and cost parameter, to a context vector. The control sequence normalizing flow takes the context vector and transforms normally distributed samples into low-cost control sequences. Our total objective is the expected cost of control sequences, the negative entropy of the sampling distribution, and the VAE loss. Is extremely high dimensional, and covering this space with training data would be very costly. Thus, we would like to adapt to novel environments outside the training distribution. To do this, we use the VAE. Decomposing the VAE loss, we see that we maximize the expected likelihood under the prior. We use this prior likelihood as a differentiable out-of-distribution score. We found that using a normalizing flow prior made this OOD score much more effective. However, we don't want to project the environment arbitrarily toward the training distribution. We would like to encode some relevant features of the environment. We encode the environment with the VAE encoder. We evaluate our OOD score for H. We then use H to generate trajectories. Unsurprisingly, many of these are in collision. To do the projection, we combine the OOD score with the cost on the resulting control distribution. This results in a new environment representation which can be used for sampling control sequences. Iteratively running this projection during execution effectively hallucinates an environment that is close to the training distribution while also ensuring the resulting samples are low cost. Our proposed projection effectively hallucinates obstacles in order to steer the trajectory away from potential collision while ignoring features of the environment which are not relevant for the current MPC task. We propose integrating our learned sampling distribution with two sample-based MPC algorithms, MPPI and improved CEM. Both of these methods sample from Gaussian distributions, shown on the left. We propose methods of incorporating samples from our learned sampling distribution for each of these algorithms. We demonstrate our approach on a planar navigation task with double integrator dynamics and a 12 degree of freedom under actuated quadrator task. In both tasks, we evaluate on challenging novel environments. We also evaluate our proposed approach for the quadrotor on environments generated from real-world data, when our method is trained only on simple artificially generated environments. We additionally evaluate on a 7 degree of freedom manipulator, using an environment collected from real-world data. We validated our approach using a real robot. Overall, we present a method for learning sampling distributions for sample-based MPC, which generate goal-directed and environment-aware control sequences, and we propose a method for adapting to novel environments. And we also show that our approach can adapt to challenging real-world environments despite only being trained on simple artificially generated environments.